Okay, so we did a little more testing. We made a couple changes. So we had run some, just for testing, we'd run a 20 gauge wire to this, and we went ahead and tripled up on those over here. So we got 320 gauges, and then this is like a number 12 or something. So much heavier wires going from the battery over to this, because we were actually getting 2 volts of voltage drop. I don't actually measure what it is now, but it's something a lot less. Anyway, we still got a dead battery. It's on dropping down to like 11.5 volts while on the charger under load. So it's pretty dead. This is definitely worst case scenario, worse than it'll actually be in a car. Okay, that said, we're putting about 17 amps a load. Kind of works out the numbers. 17 volts and 17 amps. Which is, I don't actually know if that's, you know, that's probably close to the max load it would see in a car, but I have to go check because I don't remember. But what we're seeing is we're getting 0.2 volts of drop. So with no load, we're showing 17.2, and at full load, we're seeing 17. So it's not super stiff. We're losing about 2.2 volts. That's not the end of the world if my 17 volt system was a 16.8 volt system under load or whatever. Set it up for 17.2 and it drops to 17. We'll figure it out. It's usable. And my guess is that as this voltage gets higher, it'll probably do a little better because it doesn't have to boost as much. Like the higher this voltage is, the easier it is to step up. So that may get a little better. We're going to briefly pull a board and kind of reverse engineer to see if there's anything obvious we could do to improve that. Just as an example, if the sensing element is not close to this, and then there's some lossy element that goes from the sensing element to here, you could beef up that element, just as an example. So not the end of the world, but we'll take a look at that. But this is looking okay. So we've now started and stopped this thing probably 20 times through the course of testing. Once we have a freewheel flyback diode, freewheel diode, now everything seems okay. I'm not sure if this is actually adequate. It's adequate so far, but we'll do a little more engineering and make sure we spec a really good system for the car, because I don't want to worry about that on inductive loads. And we're definitely going to be switching that's pretty much purely inductive loads that we're going to use this system for. So that's cool, looking good. I'm going to go back. So we ran this, like I said, up to 17 amps. We got to think about if we really want to do that. If we do that, I believe our original design had 3 of these, and I believe we could probably get away with 3 if we do decide to run these at 17 amps. But I got to think about if I really want to do that or not. I may decide to derate these for reliability, and that kind of throws the design off because I've already bought all the materials for a three supply system. So we'll take a look at that. But okay, after a very rough start of blowing up 2 of these, blowing up my bench supply, blowing up a diode, now we're finally getting some progress, or at least good progress. We had negative progress at first, which is also a form of progress. So now we got a plan. We're going to go back and do a little math, figure out if we want to run 3 of these or if we need to step up and run more, and go from there. All right, guys, I'll take it easy. All right, guys, I'll keep this part brief, but I wanted to show you what the math looks like. So we made this sheet a while back, and it shows the average and peak amps under different load cases. So the 17 volt system, as we can see, runs the coils, the injectors, and the ECU. That's it. No more fuel pump. Fuel pump's mechanical. Now, if we look here, you see peak output amps racing is at 45, but average output amps racing is only 29. This is because there's a case where the ignition coils, and I'll show you, if we go to coil amps versus dwell, this number here, this is our peak amps that are possible. This is when one coil is saturated and another coil is still charging, and this is at 8,500 RPMs. I did the math on this, doing dwell. This is dwell on this axis, this is amps over here. And if you add these 2 together, because at high RPM it's possible that one coil's about to stop charging, but it's still charging, and the other one's ramping up in amps. So the peak, as we can see, can actually be 39 amps going into those 2 coils. And then when you combine that with the loads up here for the injectors and the computer, that puts us at 45. However, the average is only 29. So basically that peak is only for a couple milliseconds, and that happens, it happens sometimes, but it's not average. That's just a peak draw. So the average is more like 30 amps. Now, we had assumed we could run these things at 20 amps per device. They're actually rated a little higher, but we had slightly derated them. So basically, if you put 3 in parallel, that would give you 60 amps output continuous. So that gives us a factor of safety of 1.33, and that's looking at peak amps, not average amps. So if you look at average amps, that's a factor of safety of 2. So basically, we can run even our maximum average current draw. These supplies are only doing half of what they're rated for. So I actually feel okay with that. That's probably good. And as we can see down here, all of the math we did assumed a worst case of 12.4 volts. That might sound, just for those that forgot, we're not going to run an alternator. So we're not going to have like 13, 14 volt batteries because there's no alternator. But this particular lithium chemistry, lithium iron phosphate, we looked at the math. 12.4 as a low number is probably safe. So we should be good with that. And if we look here, input current at designed output, we're looking at 84 amps between the 3 modules. So not too bad. That's about what we were seeing out here, but we were at a lower voltage. So all in all, this is looking doable. I think 3 of these is going to be okay. And because of the factor of safety, you could actually lose 1 module, and then the other 2, if they were still working, would actually be able to carry the load. These are rated at 22 amps apiece on their output. So that would give you a total of 44, and you can see our peak is 45. So that would probably work. I'm sure they can go a little over 22 for a very, very brief amount of time. I mean, we're starting huge inductive loads and they're doing that. So we could actually, this should be okay. Anyway, these things, Excel sheets can be boring, but I just want to show you guys the numbers. There's a little bit of guessing, as you can tell, because we're blowing stuff up, but we are trying to engineer this. All right, guys, take it easy. Okay, so last little update just to wrap this up. So I was Google searching, and I found this guy. Someone posted a thing. I Googled inductive loads on boost converters and something. And anyway, I came up with, someone says, hey, Google this person. He's put these boost converters together before. So I watched his video. I went to his channel. He has a few videos. I watched the latest one. Now, he says he covered load sharing. He didn't really talk about that much. But what he talked about in most of the video was filtering, or at least in the second half. So in this picture, or in his video, he's got this little circuit, and he goes over how he designed it. This guy's obviously an electrical engineer, talking about a bunch of stuff and using an oscilloscope. And what's interesting, I'm going to scroll through his video. Hope he doesn't mind. I'm not stealing anything. Credit to RF Man. But you can see this trace. This isn't even the worst one he showed. But he showed some of these traces of scoping the output of, here's some back over here in the beginning of the video. And in his video, he says the scope's at 1 volt per division. So say this in my system, this was 17 volts. This little whisker that shoots up, that's 20 volts, for example. So that's not good. I don't need 20 volts going into anything. So I haven't scoped mine to see if I have this problem, but here's what I've determined. This is going to be a future project. My car will run and drive without a 17 volt system for now. So I want to get it running because there's probably other stuff I'm going to have to fix too. And this will give me a little more time instead of just throwing this system in the car. Because if I throw it in the system the way it is, like for example this, I should have thought about this, but I didn't. So this is like one of those things that, basically it's a mistake. It's like, hey, I knew to scope it. I didn't scope it previously because I knew that when I was blowing stuff up, that if there was a high voltage spike, you can actually blow up. I was blowing transistors on the board, but I could have just as well blown the front end of my scope out. So I didn't hook my scope up on purpose until I quit blowing shit up, just because I don't want to damage my scope. But now that it's not blowing stuff up, I'm guessing I'd see something similar on my scope. So with that in mind, I'm going to hit the pause button on building the 17 volt system, but what we are going to do is when we wire the car up, we're going to put everything in place. We're going to have a spot for it. We're going to have all the wiring is going to be already routed to where once this system does exist and it's been developed and tested and we're confident that we're not doing anything bad, we're not dumping 20 volt spikes into our 17 volt system, we've really got it figured out, we can just bolt it in the car, plug the wires in, and it'll work. So that's going to be our plan. All right, guys, updates on that in the future, and back to building race car.